So hi everyone, Green's function. So today's our topic is Green's function. So Green's function is a function which used to solve a non-homogeneous second order ordinary differential equation, and Green function is treated as an impulse response of an inhomogeneous linear differential operator which is defined on a specified initial conditions or boundary conditions. So first of all, we see what is a homogeneous and a non-homogeneous differential equation means. So if I write an equation y double dash plus omega square y is equal to 0, and this particular equation is treated as a homogeneous equation, you can see that on the right hand side of the equal sign it is 0. So this particular equation we can just take it as a homogeneous differential equation. Now let me just take another example, that is y double dash plus omega square y not equal to 0, or rather it is equal to f of t, for example. Okay, f of t is some kind of function, and that means that on the right hand side of the equal sign there is non-zero value will be there. Okay, and such kind of differential equation we call as a non-homogeneous differential equations. So we have a homogeneous and non-homogeneous differential equation. Normally it is easy to solve a homogeneous differential equation, but it's difficult to solve a non-homogeneous equation. In that occasion, one can actually make use of this Green's function to solve that kind of a particular problem with a specified initial condition or a boundary condition. Okay, so normally this Green function we just represent as in terms of gene, it's g of xt, where x and t are two different variables, which is, and the Green's function is dependent on these two variables x and t. And this function is proposed by George Green in 1820s, and he has described this function is a method to solve a non-homogeneous second order differential equation. Okay, so here we see how do we execute this Green's function as a tool. And here let me just take an example of non-homogeneous differential equation of this particular form: y double dash plus omega square y is equal to f of t. Okay, and keep it as equation number 1. So this is my equation number 1, y double dash omega square y is equal to f of t. And this y double dash, as you know, this is d square y by dx square left. So that is an f of t we call as source function. Okay, we call as source function or force function, and this function is actually triggering a particular particle. If you take a single particle here, so if you trigger a force on this particle, and corresponding to with respect to that force there will be a movement towards this particle, and there is an impulse will be associated with that. So this force function we can also call as an impulse function in that case. Okay, so now if you want to find the solution of this non-homogeneous second order differential equation, so we basically, the solution of this equation means, so solution of this equation means you need to find what, you need to find y of x. Okay, so the solution of this equation means you are actually trying to find the y of x, the find out the particular function that is dependent on x or t. Okay, so that is a solution of a particular this particular differential equation. Now if I just replace this equation y of x with respect to, or y of xt with respect to g of xt, where g of xt I already said that it is a Green function representation. Okay, and there is a speciality or the property of a Green's function that L g of xt is equal to delta x minus t. Lg of xt is equal to delta x minus t, where delta x minus t is a Dirac delta function. And you know the speciality of a Dirac delta function. Dirac delta function also called as impulse function. Okay, which having only at a single point is as the maximum value, in all other point this Dirac delta function as a value will be 0. So all other point it has a 0 value. And we can see that this is an impulse function. Impulse function means on a sudden, all of a sudden you are actually applying a force, and corresponding to that force they are getting a sudden impulse or current response you are getting, so which we can actually represent as a Dirac delta function. The details of the Dirac delta function you have already covered in your mathematical physics 1 course, so I am not going very detailed into that. But what I am trying to say is that here you can see that L, where L is a linear differential operator. Okay, L is a linear differential operator. Okay, for example, let me just take L as d square by dx square plus omega square as a linear differential operator, which is operating on a green function, and the resultant will be a Dirac delta function. And that was the statement also. Here we have stated that Green's function is an impulse response of an inhomogeneous linear differential operator. That inhomogeneous linear differential operator, that is d square by dx square plus omega square, and that impulse response we can treat it as the impulse function or the Dirac delta function. So if a differential operator operating on a Green's function, the corresponding result will be a Dirac delta function. That is one of the property of a Green's function. And there are many other properties also there for Green's function that we will be discussing in the next lectures. Okay, so this equation also an important one. Keep it as equation number 2. Okay, now let me come back to our discussion. So we were discussing from equation 1. From equation 1 we know that there is an f of t. Equation 1 means y double dash plus omega square y is equal to f of t, and where f of t we specified that f of t is a what? F of t is a force function or an impulse function. So we can say that in equation 1, if I replace f of t with delta x minus t at x is equal to t. Okay, and then that equation becomes what? That equation becomes y double dash plus omega square y is equal to delta x minus t. You will be getting. Okay, and if I take this representation in terms of d square y by dx square plus omega square y is equal to delta x minus t, and if I replace this y of x, we already know that y of x means what? It is the solution of the differential equation, which I just convert in terms of g of xt, so that this equation becomes what? This particular equation becomes d square g of xt divided by dx square plus omega square g of xt, that is equal to delta x minus t. And if I take the operator out, so operator out means, so I am just taking d square by dx square plus omega square outside of this bracket, and we have g of xt delta of x minus t. And now this operator we already specified that what is this operator, that is L g of xt, and that is equal to delta x minus t. So here you can see that this operator L is already we specified. L is what? D square by dx square plus omega square. So L g of xt is equal to what? Delta of x minus t. So I'm just keeping this particular equation as equation number 3 for convenience now. So this equation number 3 is d square by dx square plus omega square g of xt is equal to delta x minus t. So if I specify the solution of the non-homogeneous equation or solution of equation number 1 as in terms of Green's function, so that I can represent, so that will be y of x is equal to integral 0 to infinity g of xt f of t dt. So this is equation number 4. So equation number 4 is the solution of the equation number 1, that is a non-homogeneous second order differential equation. We have specified y double dash plus omega square y is equal to f of t. So this is a possible solution in terms of Green's function that you can see. Now what I am checking that whether, so let me just check whether the above solution is a possible one or not. That means if I substitute y of x into that equation number 1, I will get the solution as f of t. For example, you can, if you take the first equation number 1, omega square y is equal to, so we have get that is f of t there. So if I substitute y of x is equal to this particular solution 0 to infinity g of xt f of t dt, whether I am getting f of t or not. So if I am getting f of t as the solution, then I can directly say that this is the possible solution of that particular differential equation in terms of Green's function. So what I am doing is that I'm just substituting y of x as 0 to infinity g of xt f of t dt, so that this equation becomes what? Let me just take the operator outside now. D square by dx square plus omega square, let me just take outside, into y of x, and y of x I can substitute as, okay, so here I substitute equation number 4, so that this becomes what? D square by dx square plus omega square into 0 to infinity g of xt f of t dt. Okay, so if I substitute, if I keep in equation number 5, in equation number 5, okay, so we'll get correspondingly this solution. Okay, and what will be the possible solution of this one? The possible solution of this one, so you can get as d square by dx square, that is already we know that is L. So if I take that into inside, d square by dx square plus omega square g of xt f of t dt, and we can see that from that this is d square by dx square plus omega square into g of xt f of t dt, and we have seen that this particular portion has a solution in equation number 3. That is, equation number 3 says that d square by dx square plus omega square g of xt is what? Delta x minus t. So I can replace this part of the equation with what? This part of the equation with the delta x minus t. So that is 0 to infinity delta x minus t f of t dt. Okay, delta x minus t f of t dt. Here at this point, so what is this one? So this is d square by I by dx square plus omega square y, that is equal to delta x minus t f of t. So we have an identity relation that you would have studied in mathematical physics 1. So that identity relation says that if there is a function f of t that is equal to 0 to infinity delta t minus t dash f of t dash dt. Okay, where delta is again Dirac delta function. So Dirac delta function has an identity relation, that is f of t is equal to 0 to infinity delta t minus t dash f of t dash is equal to dt, and that is what, that will be the solution. What this will be f of x. Okay, by using this, here you can see that instead of t dash we have t, instead of t we have x. So if you considering this relation, okay, we have an identity relation from let me just give it as equation number 6. Okay, equation number 6, by using that we'll get the solution as d square y by dx square plus omega square y is equal to, we'll get a f of x. Okay, sorry, okay, there's a small correction here. So this will be possibly, it should be an x. Okay, okay, so the solution will be what it will be, we'll get as f of x. So what we have proven is that, we have proven that if you use the solution of y of x in terms of g of xt, okay, so what we have proven is that d square y by dx square. So if you take the solution, if you have an equation d square y by, okay, so if you have an equation that is d square y by dx square as a differential equation, that is equal to f of x. So that is our equation number 1, and the corresponding solution can be represented in terms of what, in terms of Green's function g of xt f of t dt. Okay, g of xt f of t. So if you substitute y of x into this differential equation, and first one is a differential equation, the solution will be in terms of integral equation. Okay, and this integral equation, if you substitute into the differential equation, the corresponding solution will be f of x that you will be obtaining. So that's what we have obtained here. So we have get that if you substitute the solution back to this equation, we are actually getting the solution of that particular. So we can actually represent the solution of this differential equation in terms of Green's function. And we have also seen that one particular property of a Green function, that if a differential operator, a linear differential operator, which is also called as a self-adjoint Hermitian operator, so it is a linear differential operator, is operating on a Green's function, the corresponding solution will be, and it is an impulse function, that is a Dirac delta function. So this is one of the property of a Dirac delta function, Green's function as well. Okay, and this is a solution, this is a possible solution. So if you know the Green function, if you substitute that into the integral equation, so you can actually get the corresponding solution of a non-homogeneous differential equation. So that is the point here. Okay, so our main goal for this module is that to identify the various method to identify the Green function. Okay, the way of finding Green function. So if you can find the Green function and you can substitute back into this equation, you can actually find the solution of a non-homogeneous differential equation. And also one point to end this session, that is green function is a impulse response. As you can see that it is an impulse response of a system for a unit force applied. So we can say that it is an impulse response. That's what we can see now. This delta x minus t is an impulse function now. So when you are operating a linear differential operator on a Green function, correspondingly you are be getting a impulse response. So we can see that it is an impulse response function or impulse response of a system for a unit force applied. Okay, so that's it for today, and the next session we'll be discussing regarding the one-dimensional Green's function and different properties of a Green function. How do we can say that a particular function to be Green function? So what are the properties to be satisfied? So that things we'll discuss in the next lecture. Thank you.